Hello everyone. In this video, I am going to present my code executor, or C-executor for short. I will walk through the overall idea behind it, the core problem it is designed to solve, and the workaround or approach I used to build it. Then I will give a brief overview of the main concepts involved, explain how the system works end-to-end, and finish with a demo. So what is the main problem? In most online coding platforms, when you submit code, the platform spins up a fresh execution environment, often using Docker or a similar container-based setup. Systems like Judge Zero and many other code runners follow this model. The problem is that this introduces cold start overhead. First the environment starts, then the code runs, and only after that do you get the result. This becomes a much bigger issue for heavy workloads. Running frameworks like PyTorch is difficult in such setups, and even when GPU-backed serverless platforms such as RunPod or Modal are used, cold start is still a major bottleneck. So the key problems are, first, Docker cold start, second, messy and often painful GPU support, especially with NVIDIA GPUs, third, controlling internet access securely inside the execution environment, and fourth, the large size of container images. Now the question is, can we avoid recreating the whole environment every time? My idea is simple. Instead of rebuilding or starting everything from scratch for every execution, we can share a prepared environment as read-only and give each run its own writable execution layer. This keeps isolation, but drastically reduces startup time. The solution is Code Executor is, and here's what C-executor looks like from the user's side. You provide two things. You provide two JSON files, a request, source code, language, test cases, and an environment config, the run command and resource limits for that language. That's it. No Docker file, no image, no registry. C-executor takes that, runs the code in a kernel-level sandbox, and returns a verdict with execution time, memory, and stuttered out. The key is the shared host environment. All runtimes are installed once on the machine. No container images. A language config is 200 bytes. 10 languages is 2 kilobytes, not 20 gigabytes. Cold start, gone. Clone takes 100 microseconds. GPU, native access, no pass-through, no driver mismatch. Network, blocked by seccomp and Landlock, no IP tables. Image storage, 0. Per request cost, 1 clone, 5 syscalls, 1 exec, 1 wait PID, 1 RMDR. Modal and RunPod solve where code runs. They provision GPUs. C-executor solves how code runs safely, kernel isolation with 0 overhead. You could run C-executor on a Modal GPU node, skip containers entirely, and get both. C-executor is a sandbox code execution engine in C++23. It runs untrusted code on bare Linux, no Docker, no VMs, just raw kernel primitives. Here's the flow. A JSON request comes in with source code, language, and test cases. Main.cpp parses it, validates the payload, and resolves the language environment. Each environment is a JSON config specifying the run command and resource limits. The run command uses curly brace template substitution. Source gets replaced with the actual file path. Simple string find and replace, nothing fancy. Main.cpp hands the job to engine.cpp, which runs a fixed size thread pool. Classic producer-consumer, a shared queue, a mutex, a condition variable. Workers sit in a loop, block on the convar, wake up when work arrives. Pool size is fixed at startup, no dynamic scaling, predictable resource usage. Each worker processes test cases. For each test, it doesn't use fork, it uses clone. Clone is a superset of fork. Fork just duplicates the process. Clone lets you selectively unshare kernel resources by passing namespace flags. We pass 5. New PID namespace. The child sees itself as PID1, can't see any host processes. New mount namespace. File system changes stay private. New user namespace. The child thinks it's root but has 0 real privileges. New utest namespace. Isolated host name. New IPC namespace. Isolated shared memory and message queues. One important detail, clone requires an explicitly allocated stack. Unlike fork, it doesn't copy the parent stack. We use a thread local static buffer per worker thread, so there's no heap allocation per execution. The child then sets up 5 security layers before the untrusted code ever runs. After execution, the parent collects exit status with wait PID, compares output against expected values, and returns a verdict. Accepted, wrong answer, time limit, memory limit, runtime error, compile error, sandbox violation, or internal error. 5 independent security layers, each one enforced separately. If any layer fails, the others still protect the host. Layer 1, Linux namespaces. Already applied by clone. The child is in its own PID tree, own mount tree, own user mapping. It cannot see host processes, cannot access host mounts, and its root user maps to an unprivileged UID on the host. This is the outermost wall. Layer 2, cgroup v2. We create a cgroup for each execution to enforce hard resource limits. Memory max. If the process exceeds it, the kernel OOM kills it immediately. CPU max uses the bandwidth controller. For example, 30,000 over 100,000 means 30 milliseconds of CPU per 100 millisecond period, capping it at 30% of one core. PID's max caps the number of child processes, kills fork bombs. The C group is wrapped in a RAII guard. Constructor creates the C group directory, writes limits to control files, moves the child PID into the group. Destructor calls rmdir, which the kernel only allows when the C group is empty. Automatic cleanup, no leaks. Layer 3, Landlock. This is a modern replacement for croot. Croot changes the root directory, but it's root only, easy to escape with file descriptors opened before the croot, and it doesn't distinguish read from write from execute. Landlock is unprivileged, stackable, and irrevocable. You create a rule set, add path rules with specific access rights, read, write, execute, make directory, remove, then call restrict self. Once applied, the process cannot remove it. It applies to all children too. We whitelist tmp-work for read-write, usr-lib, and usr-bin for read-execute only. Everything else, etc proc, sys, home, completely invisible. We use inline syscall wrappers because glibc doesn't provide landlock functions yet. Layer 4, seccomp, BPF. A BPF filter program attached to the process that intercepts every syscall before it reaches the kernel. Default action is allow. We add kill rules for dangerous calls. ptrace, mount, umount, reboot, kexecload, init module, personality, userfaultfd. If a block syscall is attempted, the kernel kills the entire process group immediately, not just the thread. Once loaded, the filter is irrevocable. Layer 5, ptrace. The child calls tracem, and the parent intercepts every syscall entry. On each stop, the parent reads registers, extracts the syscall number from org-racks, and passes it to a policy function. The policy returns one of three decisions: allow, resume execution, deny. The parent rewrites org-racks to -1. The kernel returns no such syscall. The process gets a permission error but doesn't crash. Or kill, send secckill. This is the most flexible layer because the policy can be context sensitive. Allow open on some paths, deny on others, count invocations. 5 layers. Namespaces, C groups, landlock, seccomp, trace, independent, stackable, each one irrevocable. Now we get to the third and last piece of diagram, the design patterns I use throughout the code. There are 3 design patterns and a few key code level decisions. First, error handling with std.expected. There are no exceptions in the hot path. Factory methods like cgroup create return expected of cgroup or int. Success gives you a valid RAII guard. Failure gives you an ERRNO. The caller handles it with value, or monadic chaining. This is C++ +23. Expected composes cleanly, no try-catch overhead, no hidden control flow. The RAII pattern is everywhere. cgroup creates the cgroup directory in its constructor and removes it in its destructor. All guards inherit from a non-copyable base that deletes the copy constructor and copy assignment operator. You can move them, but you can't accidentally share a resource handle. This prevents double cleanup bugs at compile time. Second, the syscall policy pattern. Every syscall intercepted by ptrace passes through a policy function. The input is a syscall event struct containing the syscall number, all 6 argument registers, and the PID. The output is a policy decision enum: allow, deny with permission error, or kill. This cleanly separates the tracing mechanism from the security policy. You can swap policies without touching the ptrace loop. Third, the execution lifecycle for a single test case. 9 steps in sequence. DQ the job from the thread pool. Clone into a new child with namespace flags. Create the C group and apply resource limits. Apply Landlock file system restrictions. Load the seccomp BPF filter. Attach ptrace. Exec the user code. Collect the verdict by comparing output. Cleanup. All RAII destructors fire, C group is removed, everything is released. No manual cleanup calls. If any step fails, the destructors for already constructed guards still run. 2 more code level details. Test cases use string view pointing into mapped memory. No string allocation per test case, just a view into preloaded data. 0 copy. And the environment config is JSON based. Each language specifies its run command with template placeholders, file extension, and per language resource limits. The template substitution is a simple find and replace. Source in curly braces becomes the actual file path. That's the design. Expected for errors, RA, I for resources, policy pattern for syscall decisions, and 0 copy data handling throughout. So that was C-executor. I have shown the diagram and tried my best to explain the main idea behind it. If you want to explore it further, the GitHub link is in the description. There is also a quick demo video showing it working, and I will update that soon. Also, this project is Linux only for now because it relies on Linux-specific primitives like clone, namespaces, and C groups, so it will not run on macOS or Windows as it is. If you have any suggestions, improvements, or think I missed something important, please let me know.